Fourier transform analysis. So there are two types of Fourier. So what is a Fourier analysis, by the way? We all know, right? Fourier analysis is all about representing signals in Fourier analysis is all about representing signals in the frequency domain. Okay, representing signals in the frequency domain. So you can see there are two types of Fourier transform. Fourier transform exists only for the aperiodic signals. Okay, it exists only for the aperiodic signals, and we are trying to represent everything in the frequency domain. Okay, so signals can be continuous time, signals can be discrete time. So we will get continuous time aperiodic signals also, and we'll get discrete time aperiodic signals also, right? For continuous time aperiodic signals, we have the Fourier transform representation, something like this. Okay, we'll have for continuous time Fourier signals, we'll have a Fourier transform representation. For discrete time signals, for aperiodic signals, also we have a Fourier transform representation. The Fourier transform representation for the discrete time aperiodic signals is called as the discrete time Fourier transform. Okay, and how simple or complex it is, by the way, you can see just now we finished with the Z transform. What was the expression? X of n z to the power minus n. So here you can see your z is simply replaced by e to the power j omega. Your z is replaced by e to the power j omega. So the DTFT is nothing but your Z transform. DTFT is nothing but your Z transform. DTFT is nothing but your Z transform, where DTF nothing but your Z transform, where your Z is replaced by e to the power j omega. Okay, Z is replaced by e to the power j omega. What was the other difference, by the way? In your Z transform, you had something called as ROC, right? Every answer will be accompanied by an ROC, right? That was because in some region, the Z transform was existing. ROC was things were converging. In some places, things were diverging. The deal with the Fourier transform exists only for stable signals. Okay, the Z transform exists only for stable signal. That means the DTFT is going to occur only for signals which are stable. So there is no question of where it is stable and where it is unstable. So all those places where your ROC was diverging in your Z transform, for such signal the DTFT does not exist at all. Okay. So remember all the properties and most of the formulae, whatever that were applicable in the Z transform, they are applicable for the Fourier transform also. Okay. Now got this particular thing? Let us see a numerical. Let us see a numerical here. See, what is this thing, by the way? Alpha to the power n t of n. What is the Z transform of this thing? The Z transform of this thing is 1 divided by 1 minus alpha z to the power minus 1, right? So you can see here the Fourier transform, the DTFT is also 1 divided by 1 minus alpha z being replaced by e to the power j omega. Z is replaced by e to the power j omega. So I get e to the power minus j omega for z to the power minus 1. There is one more thing is mentioning. We remember this, it was existing only for magnitude z greater than alpha. Remember, this was existing for magnitude z greater than alpha, right? Magnitude z greater than alpha. Or this thing, alpha to the power is stable, right? For what value? See, 0.5. If say alpha is equal to 0.5, then 0.5 to the power 0, 0.5 to the power 1, 0.5 to the power 2 and all. So then it keeps, becomes a decaying exponential. For this kind of signals only, the DTFT exists. If at all alpha is greater than 1, where it is diverging, then the DTFT does not exist at all. The DTFT does not exist at all. So two things. Okay, two things. First thing is your DTFT is very, very similar to Z transform, such that your Z you simply replace by e to the power j omega. You get the DTFT. The second thing is DTFT does not exist for all the values. Okay, it exists only for those values where your x of n is stable or converging. For example, here it exists only for magnitude alpha less than 1. For magnitude alpha greater than 1, Since the signal is diverging, the DTFT does not exist. Okay, remember this thing. So then all the properties, the time shift property, all those properties will be very, very similar. Okay, so if at all you want to convert the signal, discrete time aperiodic signal from time domain to frequency domain, you have to use DTFT. Okay, which is very, very similar to your Z transform. Similarly, if at all you have the signal which is continuous time in nature, signal which is continuous but apparent. For that, we have something called as the plane Fourier transform or the continuous time Fourier transform, whose formula is given something like this. So, what is the difference here, by the way? What is the difference here? Well, you see the similarity. Do you remember the expression for the Laplace transform? X of t e to the power minus st, right? So, you simply replace s by j omega. Hmm? You simply replace s by j omega. Your Laplace transform becomes the Z transform. Your Laplace transform becomes the Z transform. Only thing is, even in the Laplace transform, it was stable for some region, unstable for the other region. The Fourier transform exists only where the x of t is converging. The Fourier transform does not exist at all where the x of t is diverging. Okay, you got the thing. So we wanted to do the analysis of the continuous time signals wherever it is stable and where it was unstable. That is why we use the Laplace. And similarly, to determine the stability of discrete time system, use the Z transform. Now, the Fourier transform is a very specific case where if at all the systems are stable, whether in continuous time or discrete time, we want to represent them in terms of frequency domain. Okay, got this particular thing? So let us see an example in the continuous time Fourier series. We remember this simple example, right? See, e to the power 80. What is the Fourier transform of Laplace transform? E to the power 1 divided by 1 plus 1 divided by a plus s, right? Is that the formula? S plus a. 1 divided by s plus a or a plus a. Now, this you can see here, this is very, very similar to your Laplace transform. Only thing is, your s has been replaced by j omega. S has been replaced by j omega. Second thing is, you can see this is a minus sign. So this wouldn't have existed for a less than 0. Would have been a diverging, right? So this thing here would have been diverging if this particular a was negative. So for that, the Fourier transform does not exist at all. For this case, Fourier does not exist. For a greater than 0, the Fourier exists. Okay, for a greater than 0, the Fourier exists. Okay, so got this particular thing. So now, so tomorrow what we are going to do is, we will start with the Fourier transform. So since you are already fresh after studying the what is it, the Z transform, I will start the DTFT first. I will start DTFT first so that we can relate it much better. Then afterwards, anyway, you are in touch with your Laplace. Using that, we will solve problems on the continuous time Fourier transform. Okay, so instead of going by the textbook method, what we'll do is first we'll study the discrete time Fourier transform. We'll get a little comfortable. Okay, all the things which we did in that transform can be done in the discrete time Fourier transform. It is much easier actually. You do not have to bother about ROC and all. Okay, you just have to find the transform. That's it. Then afterwards we will do the continuous time Fourier transform, which will be very, very similar to your Laplace transform. Okay. So that's it. Thanks for joining in. So tomorrow what we'll